Hi, I'm Matus Krajnak from Quantum Detectors. I'm an application specialist for electron microscopy. In this short talk, I would like to explain the principle of hardware-based electron counting used in our camera and advantages it brings to transmission electron microscopy. Furthermore, I'll briefly talk about the applications of our MerlinEM detector in TEM. The hardware counting in MerlinEM detector is based on Medipix free chip developed by CERN and Medipix collaboration. When a high-energy particle strikes the semiconductor top layer of the MerlinEM chip, it generates electron-hole pair cloud. A bias is applied to separate the electron-hole pairs, and in the case of electron detection, the holes are directed through the bump bonds to ASIC for analog processing and digital readout. The signal is first amplified, shaped, and then compared against a user-definable threshold. Only if the deposited energy is larger than the threshold, an event is counted. Each pixel in the setup is technically an independent detector. Okay, so what does this detector technology offer in transmission electron microscopy? Firstly, electrons are detected directly without any additional signal conversions and associated noise. Secondly, the signal is read out digitally from each pixel. This has a major advantage over the CCD or other CMOS technology as the signal is not shifted between the pixels and therefore no noise is adding by reading the chip out. Additionally, the detector contains two 12-bit counters which support versatile frame rates and counting ranges. The two counters can be used in parallel to operate the detector without the dead time. One counter can be used to count electrons while the other one is being read out. Quantum detectors supply MerlinEM in three different geometries: as a single chip, as a 2x2 quad chip, and as a 4x1 geometry EELS detector. The word hybrid and hybrid pixel detector means that the active layer can be altered for different applications, but in the case of transmission electron microscopy, a single crystal silicon is the best choice at the moment. The detector can be used with electron energies from 30 keV to 300 keV. MerlinEM detector with its number of pixels, especially in a single version, is ideally suited for 4D STEM acquisitions. This was also the first application of the detector. Instead of collecting data with a selection of annual detectors, bright field detector, or a DPC detector, a single frame can be taken for each probe position and data can be generated in post-processing. This has a lot of advantages. For beam-sensitive samples, a single dataset can be used to generate a variety of STEM signals, and therefore the sample does not have to be exposed to the electron beam as much. Additionally, techniques like tachography or DPC with pattern matching would be impossible without recording the full distribution of the electron probe. It is also possible to develop new techniques based on C-based symmetries within the diffraction patterns and others. As a side note, the data format generated by the MerlinEM detector is open and supported by open source software like LibreTem, PyXim, and others. Our software, or acquisition software, also supports virtual detection with annular, disk, or DPC geometries. Therefore, our users can have direct feedback while on the microscope for practical use of the detector and to generate the best data possible. In summary, hybrid pixel detector technology is very applicable in STEM and diffraction, and sometimes even in TEM applications. The detector is capable of collecting single electron data on black background, but also a rather intense central diffraction probe. We have installed more than 30 detectors worldwide and have more than 40 publications where MerlinEM data have been used. These can range from some basic 4D STEM experiments like I demonstrated in this talk, or others like electromagnetic field imaging, tachography, low-dose diffraction experiments, dynamic TEM imaging of graphene and magnetic crystal dislocations, and also EELS imaging. Our data format is open and the detector can be integrated to third-party systems through TCP/IP scripting. If you're interested in more details about the detector and in focus applications, please visit our virtual booth. Thank you for your attention.